All right. Now, in this example, we're told that squid and octopuses propel themselves by expelling water. They do this by keeping water in a cavity and then suddenly contracting that cavity to force out the water through an opening. So if you've ever had a water balloon that was really full of water and then you let go and it just goes poof, that's basically what squids and octopuses do to get around quickly. Now, what I have up here is a way to find if the squid gets scared, it's just floating, it's not doing anything, it's just sort of floating here, hanging out, and then a predator shows up and the squid gets scared, it's going to expel water out and it's going to shoot off really quickly. And this problem told us that they wanted the squid to go at 2.5 meters per second. So what I've got here is I use conservation of momentum, and I can do that because it said to ignore the drag force of water, meaning there are no outside forces on the system. So the product of all objects' mass and their velocities is going to be constant at any moment in time. And so I had the initial momentum of the mass of the squid in the water times the initial velocity was 0 because the squid was just floating and hanging out. And then I set that equal to the momentum later, which is the mass of the squid and his velocity going one direction opposite to the momentum of the water, which the squid shot in the other direction. So I did all of this in order to find the velocity of that water. If the squid is going to go 2.5 meters per second, how fast must the water be? Well, it must be 6.79 meters per second. And in doing that, I also had to find the mass of the squid by himself because they told us that the squid in the water altogether was 6.5 kilograms. Now, given all this information here, they ask us, how much kinetic energy does the squid create by this maneuver? And so what's interesting about this is kinetic energy is not conserved because initially nothing's moving. The squid's floating there, the water's inside the squid, and the water's floating there, and nothing happens. And then all of a sudden the squid gets scared. Pew! Goes off in one direction. Suddenly things are moving. So the squid put kinetic energy into being, if you like. Like it caused there to be kinetic energy that was not present before. So we want to know how much kinetic energy there is. So the thing you have to be careful of is that the total kinetic energy is going to be equal to the kinetic energy of the squid, of course, right? The squid's moving. But the less intuitive thing you have to realize is that the water's moving too. The way the squid moved was it shot water out this way so that it could push itself off. Kind of like if you pushed yourself off from a wall, you're pushing against the wall, and the wall is pushing back on you. It's the same type of thing is going on here. And so if you want the total kinetic energy, that's the kinetic energy of the squid plus the kinetic energy of the water. Remember, kinetic energy doesn't have a direction like momentum does. It can't be pointed in some direction. Kinetic energy is just an amount of energy. And so remember, the formula for kinetic energy is half the product of an object's mass and the square of its velocity. So this first thing is going to be 1/2 mass of the squid times the velocity of the squid squared. And that's going to be added to 1/2 the mass of the water times the velocity of the water squared. And so if we do that, we're going to have 1/2 mass of the squid by himself is 4.75 kilograms times his velocity squared, so that's 6.79 meters per second squared, plus 1/2 mass of the water, which was given to be 1.75 kilograms, times the velocity of the water. So notice this is the velocity of the water, the 6.79 meters per second. This right here is supposed to be the velocity of the squid, which was given. It was 2.5 meters per second. And it's very important which one goes where because notice the mass of the squid is different from the mass of the water. So learn from my mistakes and don't make them. So here we have 1/2 mass of squid, velocity of the squid squared, plus 1/2 mass of water, velocity of the water squared. So if you've got your handy dandy calculator, feel free to throw this stuff in there. If we do this first one right here, the squid's kinetic energy is going to be 14.8 joules, and the water's velocity, notice it has a greater velocity, and when we're squaring stuff, sure, the water has less mass, but because we're squaring something that's, 4 meters per second larger than this, that's going to be a much bigger difference. And so the water has 40.3 joules of kinetic energy. So of course, if we add those, we do that right here. If we add those together, the total kinetic energy, 14.8 plus 40.3, that's going to be 55.1 joules. So there we go. The kinetic energy of both the squid and the water all together is going to be 55.1 joules. It doesn't matter if the squid's going one way and the water's going the other way, because we're just talking about all the energy in general, regardless of which way it's going, which, it's not really going anywhere, it's just the amount of energy in these objects. And so that is the numerical result. I just wanted to point out that I went to joules here. And so we had kilograms, meters per second squared, and then all of a sudden I switched my units to joules. If you have a physics teacher like mine, he might not like you just doing that. He'd want to see, how do you know that's joules? Are you sure that's joules? You know it's supposed to be joules because it's energy, but do you know it is? And so I just want to show that, well, if you take these units here, you've got kilograms, square a meter per second, you get a meter squared per second squared. Okay, well, a kilogram meter per second squared, well, remember that force is equal to mass times acceleration. So mass, kilograms, times acceleration, meters per second squared, that's a Newton. So you've got a Newton times a meter. Well, recall that's what a joule is. A joule is a Newton meter. And so there you go. The units switch over because they are equivalent units, and you can work with them algebraically and using what they're defined to be as, just as you can with numbers, basically. So make sure you're comfortable with that, and you don't just assume that the units are correct because that's what you're supposed to get. So there we go. If the squid shoots off in one direction at that speed and the water shoots off in another direction at this speed, this is the total kinetic energy created. And that is this example.